Hi, welcome back. In this video, we're going to talk about applying the quadratic function to real-life scenarios. So we're going to be looking at real-life applications of a quadratic function. The goal is, as we apply this quadratic function to a real-life situation, is to interpret the meaning of the attributes. If you are not familiar with the following attributes, I strongly recommend you to watch the previous video on quadratic attributes, where we discuss vocabulary words like vertex, maximum and minimum. We talk about rocks as x-intercepts, roots, zeros, solutions, y-intercept. We talk about domain and range. We talk about a lot of different attributes of a quadratic. So you want to make sure you're familiar with these vocabulary words so that we can now apply all of these words and other ones to real life context. Okay, we'll do an example of a real life situation, analyze all of these different attributes and how they pertain, how does this quadratic make sense in real life, and what is the meaning behind it. If at any point you find that this video is useful, go ahead and click the like button. And if you haven't subscribed so already, go ahead and subscribe so now so you can have access to more videos like these. All right, let's begin. Here we have a situation where Luis kicks a soccer ball. The graph below shows the height of the ball over time. The first thing you want to do when you're looking at situations like these is you want to make sure, if there's a word problem, is to read it and get very familiar with it. And then you want to look at the graph. You want to identify what the x-axis represents. What does the y-axis represent? And then make sense of the situation. Does it make sense for, I don't know, Luis to be standing here? I'll draw as best as I can a Luis guy kicking a soccer ball. Does it make sense that he can kick the ball and then eventually the ball will follow a specific path? Okay? The x-axis represents how much time, the y represents how high in off the ground it is in feet. And then once you better have an understanding of it, like, let's answer this question. What conclusions about the path of the ball can you draw from the graph? There's a lot of things you can look at here. Like, what's the maximum height of the ball? How long does it take for the ball to hit the ground? What is the initial height of the ball? There's a lot of different things we can look at here. Okay, so we're going to be able to answer a lot of questions here, at least 5-6 questions on just looking at this graph and interpreting the meaning of it. Word problems are the thing that people usually dislike the most about math. And these are usually the ones that are not the hardest to answer. So if you take your time to read the word problem and just analyze the picture or the graph, you should be able to answer the rest of the questions with a little bit more ease. They're not as difficult as people may make it seem. So let's go ahead and answer a few questions regarding this same graph. The first thing that I want to look at, as I said earlier, is what does the x-axis represent? Right? The x-axis represents the number of seconds, right? How much time has passed since Luis kicked the ball. So we're going to say that this is seconds. Okay, if I know how to read the x-axis, I know what it means when it touches the x-axis. The y-axis here represents what value? If we look at the y-axis, units are going to be very important, right? The height of the ball is in feet. So the ball will travel up into the air and it'll start coming back down till it hits the ground. Usually in real life situations, the bottom represents how much time or represents the ground aspect of things, and the other one represents the height of what something travels, like a rocket or a soccer ball or something being launched into the air, right? Because it has to go up and then eventually it has to come back down. So the y-axis here represents the feet of the ball, or the height of the ball in feet. Okay. Now let's talk about the starting height of the ball. The starting height will always be represented or known as the y-intercept. In a real life situation, because we don't have any negative numbers, right? There's no negative x values in real life situations. The beginning of the graph here, the y-intercept, is usually where something begins, where a rocket is launched, where a ball is kicked, where a rock is thrown. It'll always represent here. So wherever it touches the y-axis, that's the beginning of the word problem. So here, the height of the ball is down here at the bottom. So we can say, because it starts here at 0, the ball is 0 feet on the air. What does that mean? It means that it starts on the ground. The ball is kicked from the floor. And the y-intercept always represents the beginning. So initial height, initial time, initial everything. Here, question number 5. The ball reaches a maximum height of approximately how many feet after how many seconds in the air? So we're interested in here in the maximum height. Now, a key word that we want to pay attention to from a previous video is maximum. What is the meaning of maximum? Here, the maximum represents the highest the ball will ever reach, that point up there. See if I can circle it better. That point right there represents the maximum height. So what is the maximum height of the ball? What we're really looking at here is this point right here. If we look at the point, it's going to be at 1.5. Let me change the direction a little bit so we can fit it. .5, comma, about 38 is what I would say is where it's at. A little bit below 40 and higher than 35. I say 38, 39, right? We're looking at the maximum height. Now, since height represents the y value, the ball reaches the maximum height at 38 feet. So that point, we're interested in the y value because that represents the y-axis. The height is in feet. We're looking at 38. How long does it take for it to reach that height? Now we're going to look at the time. The time is the x-axis. So the time here is 1.5. So after about 1.5 seconds, it will reach the maximum height of 38 feet, and then eventually the rest of the time it'll take to go back to the ground. Again, if you pay attention to the x-axis and the y-axis, then we can answer the question we're interested in, right? We wanted to know the height. So we look at the height or the y value. Then we wanted to know how much time. So we're looking at seconds, which represents the x value. So here we want to know what happens, right, when the ball goes to the ground. The ball returns to the ground after how many seconds in the air? If we know that the ball starts here on the left at 0, how much time does it take for the ball to hit the ground? Time represents the x-axis, so it takes about 3 seconds for the ball to hit the ground. However long it takes to hit the ground from the beginning to the end, the halfway distance will always be the point where it reaches the highest point, always. It should take double the time, right? Half the time to go up, half the time to go down. That's what makes parabolas so symmetrical. So if it takes 3 seconds to hit the ground, it means that halfway there, it reached the highest point. How long was the ball at least 20 feet off the ground? So we're interested where along the way, how long was the graph above 20 feet from the floor? So we know that it reaches 0 here, 20 feet at this point. It goes up into the air to 38 feet. It starts to drop. It hits 20 feet again, and then it starts to fall below 20 feet till it hits the floor. So I am interested in the part where it's always above the ground, 20 feet. So it starts here and ends here. Let me see if I can make this a little thicker so you can see it better. This part of the graph is when the ball is 20 feet off the ground. Everything that's not shaded in the graph is when it's below the ground or below the 20 feet. And since we're interested in for how long was the ball in that range, we're going to look at from here From here to here, the ball was in the sky, above 20 feet. So from 0.5 seconds to 2.5 seconds. How much time is that? From 2.5 and 0.5, all we have to do is subtract. 2.5 minus 0.5. The ball was above the ground, at least 20 feet into the sky, for about 2 seconds. I'm going to put an approximate symbol. 2 seconds. It's an estimate. All right, last scenario. Now we're looking at domain and range. We look at the scenario and we're interested in what is a reasonable domain and range. And the reason why we say reasonable is because the domain and the range for any quadratic would be if this continues forever. But because it's a real life problem, that would entail, right, if we have arrows in this situation, it would mean that the graph would actually go down and exist in negatives. The ball starts here. There's no negatives in the graph. Also, once it hits the floor, the ball's going to keep bouncing. It's not going to go underground, right? So we don't want to look at from negative infinity to positive infinity. We don't want to count the arrows going under the ground. When we say a reasonable domain and range, we're talking about in a real life situation, what are the parameters that we're interested in? So we cannot just we can't just look at a graph and say that there's arrows. In this special situation, we have to make sure that we have endpoints. So it starts here and it ends here. Now let's look at the domain. The domain represents the x values. The range represents the y values. So for domain, we're looking at everything on the x-axis between 0 and 3 seconds. And that's what we say. X is between 0 and 3 seconds. The range is the y-axis. The y-axis, I'm going to do this in a different color. On the y-axis, we start here at 0, and what's the highest point that it will reach on the graph? The highest value that this will exist is over at 38 feet. So the range will go between 0 and 38. The maximum value on the graph, the max will always determine the range. So it's everything below it, everything below 38. But it doesn't go to negative infinity. It stops at the ground. So we can't just say it's everything less than 38. We have to say it's between 0 and 38. That's why we put the y between those two values. All we're really doing here, guys, is we're taking a real life situation and we're applying it. We're applying the vocabulary words that we're learning to this real life situation. So to sum it up, here's an example, right? Here's a different example, completely different example. Feel free to solve this for extra credit if you like. But the idea here is read the word problem, what's happening, look at the graph, identify the x-axis, the y-axis, try to picture the scenario of what's happening. I know it looks like there's a lot to read here, but it's really just describing the situation. If you understand the situation, the better you understand the situation, the easier it is going to be to make sense of the graph or the problem. So word problems with quadratics comes down to just understanding, do you know what's happening? Try to picture the situation. Try to draw a person over here standing or a building. Try to draw what's happening so that you understand what the questions mean when it says, what does the x-axis represent? What does it mean when it hits the ground? Where does it start? What is the highest that it's going to reach? How long is the ball in the air? Or in this scenario, the rock, the stone. So take time to think about stuff, look at the graph, analyze the x-axis, the y-axis, and the rest is just making sense of it in a real scenario. I hope this has helped. If it did help you, don't forget to click the like button. If you haven't subscribed, do so already. And as always, we'll calculate later.